everyone. Hello again. So now the Pablo will give us the second part of the algebra seminar. I mean, the main part of the seminar. So Pablo, yeah.
Thank you. Okay, so let me see if I can. Did I mess up? Am I still able to share stuff? I had a message, and I don't know if I did it correctly. Okay, excellent. Looks like it's good. Fantastic. So yeah, thank you. I'm excited to now talk some more about like actual research that is my own, and I'm not just citing people that came before me, which I will also be doing. So what I'm going to be talking about today is Hochschild cohomology of general twisted tensor products. So first, I'm going to motivate a bit, like why would you care about Hochschild cohomology and why would you care about twisted tensor products? So if you've been to the previous half an hour, then some of this will resonate a lot. And then I'm going to be defining Hochschild cohomology for K-algebra. So again, if you've been here the last 40 minutes, you'll know what all of this is about. And then I'll hopefully tell you something that you don't know. I'm going to be defining twisted tensor products, and then I'm going to give you some of the results that we found concerning their Hochschild cohomology, namely their Lie algebra structure. And finally, I'm going to give you some of the applications. So let me begin then by an introduction to all of this. So throughout this talk, we'll be in a slightly different setting that's before. Now A will still be a unidal associative algebra. But now K will be a field. So in this setting, as we have previously discussed, the Hochschild cohomology of A encodes infinitesimal information about the algebra. More specifically, the zero cohomology, the first Hochschild cohomology are the outer derivations. And then the second Hochschild cohomology, I will again not give you the object, but these are the important infinitesimal deformations. So, as promised, let's talk a bit more about what are parts of A, and I put them in together somehow to get only one copy of A. Given this multiplication, I can change it a bit, and by a bit I mean I can change it as a through a polynomial, and maybe when I just plug my indeterminate to be 0 or 1, the original multiplication, or I can even perturb it as a power series. So an infinitesimal deformation is one of these deformations that is small. So I'm just changing my multiplication a tiny bit. And what I mean by the important is that my deformation, when I get my multiplication and I perturb it, maybe I get something that is isomorphic as an algebra to the original thing that I had, or maybe I get something different. So and my important infinitesimal deformations are the small ones that give me something different. So I'm essentially quotienting out by the deformations that give me the same to what I started with. So that's the object that, or the construction that I'm going to be looking at. And then the objects that I'm going to apply this construction are the twisted tensor products that I decorate with a sub tau, right? So it's A tensor sub tau B. Those are my decorations. And these guys were introduced by Kapp, Hochschild, and Banzura when they were studying non-commutative tutori. And they found out that whenever my original algebra over a field has an underlying vector space that is given by a tensor product of two subalgebras. Then it is isomorphic to one of these guys. So even though this originally came from a very specific study in non-commutative geometry, they wanted to sort of be able to separate non-commutative spaces. This, in fact, is an immensely general construction. So examples of twisted tensor products can be found everywhere. So for example, cross products of C-star algebras with groups, or cross products with Hopf algebras, or algebras with triangular decomposition, such as universal enveloping algebras, or Lie algebras, or quantum groups, or braided tensor products that are defined by R matrices, right? So it can they satisfy like this Yang-Bactric equation, or many other byproduct constructions. My point is that you will be hard pressed to find an algebra that is not a twisted tensor product. So this means that this has applications all over mathematics. Some of them, as I mentioned, C-star algebras are operator algebras. From the study of non-commutative tutori, maybe you can already hint that this is very much related to algebraic topology. And well, my favorite, which is quantum symmetries. So keeping this in mind, and for those that know what Hochschild cohomology is, but since I'm talking about it, I am sort of forced to introduce it anyways. Let's go to the second section, the second part of my talk to define it. Now, since my algebra is over a field, I can sort of exchange my definitions and first just claim that the nth Hochschild cohomology of my algebra A is just the nth Xed group. over the enveloping algebra of A with coefficients in A, right? Where let's remember that the enveloping algebra is A tensor A up. So essentially everything as before is considered as a bimodule over A. And again, if I just take all of these and I add them up, what I get is the full Hochschild cohomology. And well, this is a pretty clean definition, right? As it's much cleaner than what we saw before. And again, the fact that case of field, it is heavily used. So if we want to express the above, like the construction that we saw, and that I'll go back to briefly in a few seconds. If you want to see that construction as an X group, what we actually need is something called relative homological algebra. So we are leaving the realm of like the usual homological algebra, and we require that our exact sequences or complexes and every construction has some form of splitting. So it gets much messier if the algebras are not over a field, but here everything will be over a field. I just want to let you know that this can be generalized and things do get substantially more complicated. So if we want to compute these guys, then what we need is, well, a resolution. And as we saw, for both defining utility and historical reasons, a relevant one is the bar resolution. And this comes from considering multiple copies of A, let's say n plus 2, as a bimodule by multiplication on the outermost factors. Okay, so we have like those two copies of A sandwiching n copies of A, and we multiply the outside. And what we do is just put all of these guys one after the other. So D3 lands in 4 copies of A, D2 lands in 3 copies of A, D1 lands in A tensor A, and then when we multiply them together, we land in A. And again, the differential is just taking n plus 2 copies of A and successively removing the tensor products and multiplying in an alternating fashion what lies in between. Excellent. And again, this holds for all these elements inside of A. So again, this is the augmented bar resolution because we have like this extra A, but we can just remove it and do computations with the usual bar resolution. And when we are working with the usual algebras, this turns out to be a projective resolution. In particular, when we have a field, this is actually a free resolution. But when we're working with special algebras or special families of algebras, they usually have tailored resolutions that are more convenient to use for them, right? So this is a resolution that exists for any algebra, but maybe if our algebra is causal, we can use its causal resolution, or if we have a complete intersection, we can use a finite free resolution, or if we have a monomial algebra, and for me, a monomial algebra is some quiver algebra modulo some paths. Maybe the paths have degree 2 or length 2. So maybe for such a monomial algebra, we can use something called the bar cell resolution. So a canonical problem in the Hochschild cohomology of algebras is how to transfer some information that we have in the Borel solution that we can define for all algebras, transfer it to the specific resolution tailored to some family of algebras. And why would we want to do this transfer? Like, what are the benefits of working over the Borel solution? It turns out there are two operations that are natively defined on the cochains of the Borel solution. And those two operations are the cup product and the Gerson-Haber bracket. So what the cup product does, it takes a cochain of degree n and a cochain of degree m, and it splices them together to give a cochain of degree n plus m. And what the Gerson-Haber bracket does is it takes the same domain, but the target switches a tiny bit. So instead of landing in degree n plus m, we land in degree n plus m minus 1. So we see n 1, but then we land in n plus m minus 1. So there's a shift of 1. These operations can always be defined cohomology, a couple of structures. The cup product gives the full Hochschild cohomology as structure of a graded algebra, and the full Hochschild cohomology of a algebra. So if we take the full Hochschild, what we get is a graded commutative we take the bracket we get a graded Lie algebra. And they satisfy a few compatibility conditions. They satisfy the graded Leibniz rule, namely, which means that the full Hochschild cohomology with both operations has the structure of the so-called Gerson-Haber algebra. This is also known as Poisson 2 algebra, or a Poisson algebra with Poisson bracket of degree -1. But usually in this context, we call it Gerson-Haber algebra. But there are three names for exactly the same object. And the way in which we can think of this Gerson-Haber algebra is we can just think of it as a graded Lie algebra coming from an associative algebra, where my associative algebra is just this cup product. So this is like a way of like intuitively thinking about this, and this is definitely not true. This is just an intuition. And it's not true because we have like this shift of -1. So the degree of the cup product or the homological degree is different from the Lie degree, right? Because we need this shift in -1. But we can intuitively just think of it as a Lie algebra coming from an associative algebra. So given this brief overview of Hochschild cohomology, let's jump to twisted tensor products. And these guys are those very general constructions that generalize well, essentially, I don't want to say all, but many of the constructions that we care about in algebra. But this construction is rather easy to understand and is nothing more than a non-commutative generalization of the usual tensor product. That's all what it is. So how would we go about defining a non-commutative tensor product? So we should start with two algebras. Algebras over a field, just to make sure that nothing is going wrong. And then we would like a way of permuting them. And we call that a twisting map. And what my twisting map does is it permutes my algebras B and A in a way that is compatible with the algebra structure of A and B, right? So in particular, this guy needs to be bijective and linear. And this would just be the usual permutation of elements in the usual tensor product. But we want to make it a bit more general. So let's just take tau to, again, preserve the algebra structure of B and A. So to do that, they need to satisfy that they are compatible with the units and that they are compatible with the multiplication. So let's forget about A and B being associative yet. Let's take them as unital algebras. So what does it mean that tau is compatible with a unit? So hopefully that means that if I have a unit that is being tensored with any element of A, and I want to twist B past A, the unit preserves the elements. So twisting with a unit is doing nothing. And similarly, twisting with the other unit also does nothing. But this is not good enough. This is just good to preserve units. How about preserving multiplication? To be compatible with the multiplication, we would need to be able to multiply B and multiply A. So I need at least 2 copies of B and 2 copies of A. And hopefully what will happen is that multiplying and twisting fits. So let's draw that in a diagram. So if I start with 2 copies of B and I add 2 copies of A, I can first twist everything past each other. So I can apply my tau in the middle, and I can permute the innermost B and A. I can then again apply tau on the outermost factors, and I permute B and A twice. That's an ugly B. Let me make it a bit prettier. Then I can yet again permute the innermost B and A and now I'm in good shape to multiply. I multiply my A's and I multiply my B's. But I could also have done it the other way. I can just first multiply and then twist. So I have a diagram. My diagrams should be commutative. So let's just impose that. Just to be extremely clear about this, we are first twisting and we are then multiplying. And hopefully that's the same thing as first multiplying. And then twisting. So once that we have such a map, we can just define multiplication on the vector space given by a tensor B. This multiplication is what we all want to do, right? We just permute the innermost element and then we multiply. And that's what's called the twisted tensor algebra. And it is denoted by a twisted tensor product B. And as I said, is a tensor B as vector space with multiplication given by first permuting the innermost copies of B and A using the twist, and then multiplying A's together and the B's together. And well, this turns out to be an associative algebra. If A and B are associative, and I remember that my A and B's were associative algebras, then this multiplication turns out to be associative. So if my title is not misleading, then what I want to understand cohomology of these guys. And I again take this twisted tensor algebra as a given algebra, but to use information of A and B to obtain information of the twisted tensor product. So for example, if we have that A is causal and B is also causal, maybe there is a way of merging the causal resolutions and we get a resolution that may or may not be causal. In general, it will not, of the twisted tensor product. In particular, what we want is knowing this Lie bracket in the Hochschild cohomology of A and knowing it in the Hochschild cohomology of B. We want to obtain the bracket in this Hochschild cohomology. And something that is useful to do this is construct modules for the resolution of this twisted tensor algebra, knowing resolutions of A and B separately. And this can be done, and it requires some compatibility conditions. So in the same way that I have a notion of the twist being, if I get a bimodule of A and a bimodule of B, I have a notion of my bimodules being compatible with a twist. Namely, my module action and my twist commutes, and also there's a commutation relationship with the multiplication of all my algebras when I apply the twist. So I can do this again, not just for modules, but for solutions of bimodules. And there is a way of understanding the two resolutions of bimodules to be compatible. Essentially, what all of this amounts is that in the same way that here I want to take B and A and pass one to the other side of the other, when I have a bimodule of A, I want to be able to permute it with B. When I have a bimodule of B, I want it to permute it with A. When I have a resolution of, for example, A, I want to be able to just permute the resolution with B, and so on. So this gives a ton of compatibility conditions that when they are satisfied, it turns out that we can actually obtain projective bimodule resolutions from projective bimodule resolutions. And this is not easy to see. we need to work hard. Look at who came before us. In this case, the spoon. And they prove that under all of these compatibility conditions, a projective bimodule resolution of the twisted. This is actually a projective bimodal resolution, but this construction essentially amounts to a total complex. So how restrictive are these compatibility conditions, right? Because maybe just something or that is never really useful because the compatibility conditions are never satisfied. That is not the case. This is indeed very useful because the compatibility conditions are satisfied for the bar resolution. All twisting maps. And the causal resolution, so if A and B are causal, their causal resolution is also compatible with a caveat. This is only compatible with strongly graded twists. So a graded twist just takes something in degree n and lands in degree n. Strongly graded means that it preserves the degree in each A and B. So if I have something in degree I in B and something in degree J in A, I permute them and I land in degree J in A and in degree I in B, right? So my degrees are preserved in each A and B, which is much, much stronger, right? This is very much a restrictive condition. And this is something that it's maybe not too desirable to do. And that's why we tackled some of the applications wherein the twist was not strongly graded. So let me build up to that by telling you some of the results that we obtained. And here I should cite people, especially because I'm being recorded. So let me see. So this is definitely we definitely use the work of Chris Negron and Sarah Witherspoon. I already mentioned Shepler and Witherspoon. We generalized. We're heavily inspired by work of Grimley, Nguyen, and Witherspoon. And what we do is definitely covered under the framework, even though we didn't explicitly use it, of Yuri Volkov. Okay, so now I think I'm safe. So let me tell you what we proved. So what we did is, well, like having all of those compatibility conditions being in the resolutions, that's very much not nice. We don't really want to work with specific resolutions that need to be so compatible. We just want to work with general solutions. So let's pick any two general resolutions. So let's P be a resolution of A, and Q be a resolution of B projected by modular resolutions. Such that we sort of translate the conditions, the compatibility conditions on total complexes. So we want this guy to be nice. And what do I mean by nice? By nice, I mean co-unital DG coalgebra. So we have like we want some co-unit and we want like a diagonal map. But that is a fairly general setting. There are many resolutions that are co-unital DG coalgebras. So this is a rather mild restriction. And then what we also want is an isomorphism between 3 total complexes. So we do this construction, and then we do the total complex with respect to the twisted tensor algebra with the same construction. We want this to the construction obtained when we apply it to 2, and this should be 2 total complexes. And in this specific case, what is a chain map isomorphism? And it also has to satisfy some technical conditions that include being a lifting of the degree -1 canonical isomorphism. So in degree -1, these 2 triple total complexes have the same. They can be they can be augmented with 2 objects that are canonically isomorphism from multiplication. So this sigma needs to lift, among other things. It needs to lift that canonical multiplication. And this may at least as general as the construct in second. But even as general as we want, and we are able to obtain a co-unital DG coalgebra on this tensor product, and we are able to get such a chain map isomorphism with all the technical conditions that I am sweeping under the rug, and then we can give an explicit formula for the Lie bracket. Emphasis on the explicit, right? It's a closed formula. There you go. So that's very nice. Like we were able to like obtain such a bracket in many cases. Useful. So the conditions that we required are satisfied for some big families of examples, namely this theorem also applies for both the bar resolution and the causal resolution for strongly graded twists. So this is indeed at least as powerful as the constructions before, but our formulas, our explicit formulas, they're actually applicable in full generality. The Barber solution always exists, which means that this formula always computes the Lie bracket if you just apply to the Barber solution. Which is always nice to have, just like a way of computing this Lie bracket. However, we were not fully satisfied by the fact that we still have like this pesky strongly graded twist condition over here. Unfortunately, we were not able to do best like in full generality. I can, hopefully I'll have time to get back to that in a second. That is ongoing work with one of my co-authors. So we tried to apply this to a specific example where tau is not strongly graded. And it turns out that our techniques are useful for crossover solutions when the twisting map is not that well behaved, at least in one other case. So the so-called Jordan plane. And this is the free algebra in two variables where we mod out by the commutator minus x squared. And this looks a bit like a twisted tensor product if I just take A and B to be polynomial algebras. And I get my tau to just permute x and y. So this is definitely not strongly graded because here we have degree 1, degree 1, degree 1, degree 1, and then I am landing in something that has degree 2. So this x squared is what is making this tau not strongly graded. So in principle, we can't just apply what we found. We need to work a tiny bit more. So before I get there, let me say why this may be of relevance. So if we look at the Artin-Shelter classification of algebras, the Jordan plane is one of only 3 types of algebras of global dimension 2. The other 2 are the algebra, the free algebra in 2 variables, the square of one of the variables, maybe x squared, and the other one is the quantum plane or the skew polynomial when we multiply by some element of the field, right? So there's only 3 of them, and the Gerson-Haber algebra structure, this Lie algebra structure, remained unknown for the Jordan plane. It was known for the other 2 for maybe like about 30 or 40 years ago is when they found them, but it remained unknown for this specific case. And it was first computed by Lopez and Solotar in 2019. And what they did required very heavy machinery. So without getting into the details, what they did is use a resolution, like a very specific resolution that's similar to the Annick resolution. And then they used methods specific for derivations. So since it's an algebra of global dimension 2, we only have degree 0, 1, and 2 to like account for. And as we saw in degree 1, those are the derivations. So we can understand what is going on in degree below, below 1 by looking at the derivations. And then we need like to invoke some spectral, or they needed to invoke some spectral sequences and do like some further reasonings to see what happened when we get the bracket for an element in degree 2 and an element of degree 1, which is also landing in degree 2. my point is that that was very heavy machinery that we circumvented completely by using these techniques. So what we proved is that if we take the technical conditions, so we like manually check essentially those conditions, and then we apply the theorem, and this provides an explicit description of the Gersten-Haber algebra structure. Again, emphasis on, well, so since this seemed to be a bit twisted tensor planes. So elements of this form where the twist is just graded. We make no assumption on the twist being strongly graded. And that is work in progress. And hopefully I have a chance to talk about this in the future. And this being said, thank you for your time.
Thank you, Pablo. Any questions? I have a quick question, Pablo. So let's have a bracket 0. Unit of the Gersten-Haber bracket 0.
I'm sorry, I think my connection is unstable. So it says, could you please repeat the question?
Yes. So do you know examples of algebra so that the Gersten-Haber bracket is 0?
So a recent work by Tekin Karadag on his own. So he checked the Gersten-Haber algebra structure on the Taft algebra. And in many cases, those are 0.
Oh.
Or also in polynomial rings, those are almost always 0.
Mm-hmm. I see. But in your algebra, these are not 0. I mean, you computed, right?
Absolutely. So in the Jordan plane, in general, those are not 0. If you take any two cochains, the bracket will not be 0. That's part of the difficulty where like it came in computing it, because it was not 0.
I see.
So finding formula is a challenge.
Yeah. Any other questions? Okay, well, let's thank the Pablo again.
Thank you very much for having me.
Yeah. Well, then see you next time.